Hi everyone! Salamat sa inyong patuloy na ginagawang pagsubaybay dito sa ating discussions about mechanics of deformable bodies. And our topic for today is about simple strain. This is caused by the deformation when a body is subjected to a load. And to start our discussion, let us have the definition of what strain is. Let us imagine that we have a bar of uniform cross-sectional area A and a length L that is being subjected to an axial load P. Aside from the stress that the P will cause upon the bar, whose magnitude is equal to the ratio of the load P to that of the resisting area, which in this case is our cross-sectional area, the bar is also subjected to an axial deformation. And to illustrate, here is our bar that is subjected to an axial load P. The bar has a total length equal to L and a cross-sectional area equal to A. The first effect that this P would have upon the bar is our stress, which is defined as the ratio of the applied load to the resisting area or the cross-sectional area of the bar. In symbol, we take that stress as the ratio of the P over A, where P is the axial load, area is the resisting area, or in this case, the cross-sectional area of the bar. Now, aside from this stress, the bar will also be subjected to a deformation caused by this load P upon the bar. And to show that deformation, let us have here this deformation. Okay, do you see that deformation? I will ipakita ulit natin, ano? Ito yung deformation. Okay, humahaba yung ating bar when the bar is subjected to an axial load P. And by definition, okay, we define unit strain as the ratio of the deformation to the original length. The ratio of this deformation to that original length is called as the unit strain. In symbol, we write this as strain equal to the ratio of the deformation to that of the original length. Isa sa mga importanteng maunawaan natin ay ano ang relation ng stress at strain when a bar is subjected to an axial load P. And this can be viewed and illustrated by means of the stress-strain diagram. Ano ba itong stress-strain diagram? Ang stress-strain diagram daw ay isang curve that is used to illustrate the relationship between the materials, stress, and strain. Siyang ginagamit natin para ma-explain natin ano bang relationship mayroon ang stress and strain when the bar or the object is subjected to a load P. The stress-strain curve can also be constructed from the data obtained in any mechanical test where the load is applied to a material and a continuous observation and measurements of stress and strains are made simultaneously. Sabi nga, para ma-drawing na natin or may construct natin yung itong tinatawag na stress-strain diagram, we take a continuous recording and observation of the stress and the strain when an object is subjected to a load. When a ductile material like a mild steel is subjected to a tensile test, then the material will pass through various stages before fracture or before it fail. And these stages are the following: the proportional limit, the elastic limit, the yield point, the ultimate stress point, and the breaking point or rupture point. These stages will be explained later on as we will be discussing also how do we construct the stress-strain diagram of a material when the material is subjected to an axial load. And I have prepared here an animation para maunawaan natin kung paano ba i-construct itong stress-strain diagram at maunawaan natin yung different stages na kung saan ay dumaraan ang ating bars or body or object when that object is subjected to a stress. And here is our example. Ang example ng drawing ng stress-strain diagram ay sa pamamagitan ng pagsasubject ng ating material sa tinatawag nating axial load. At ang makikita natin dito ay isang example ng isang universal testing machine na ginagamit to test the strength of a material, and from here, the stress-strain diagram is drawn. Ganito ang mangyayari sa ating bar kapag ang bar ay na-subject na sa load, that is applied by the universal testing machine. Makikita natin dito na itong ating stress ay mag-increase as the P increase. And as the stress is increasing, the bar will also be subjected to an elongation that would be represented by the movement of this gauge in this direction. Here is what will happen. Nakikita niyo, itong kulay pula nito represents the diagram that shows the relationship between the stress and the strain. So, dinaanan niya itong isang stage nito, which represents the proportional limit. Then, dumaan din siya sa another stage, which is the elastic limit. Then, we have the yield stress limit. Then, the ultimate. And then, finally, the breaking point. And you would see that the stress increases in this direction while the strain moves in that direction. Habang nag-i-increase ang stress, nagkakaroon din ng movement itong ating bar. So ulitin ko at tingnan natin kung ano nangyari dito sa load na ito. Pati yung load pati dito ay nag-i-increase din. So let us do it again. So here is what will happen. Habang tumataas yung load, tumataas ang increase, humahaba siya, dinadaanan niya yung stage, itong tinatagting proportional limit. You have the elastic limit, you have the yield point, and afterwards, aakyat siya hanggang sa marating niya yung pinakamataas na value representing this value here. Then afterwards, pag bumagsak na, that actually an indication na mapuputol na siya, and then finally, the breaking point or the rupture point of the material. So to explain the different stages, ganito yung nangyari, So, habang tumataas siya in this direction up to this point, mapapansin natin that the stress and strain are directly proportional to one another. There is actually a relationship that this curve represents a straight line. Up to this point, which is called what? That point is called the proportional limit. Na sinasabi, the proportional limit is point on the curve within which the stress is proportional to the strain. Makikita daw natin dito na hanggang sa area na ito, within this limit, ang stress daw is proportional to the strain. At makikita yan sa pamamagitan ng straight line of the curvature. And the stress up to this point can be also known as the proportional limit stress. At iyan ang pagbabasihan natin ng derivation ng relationship between the stress and the strain. At itong slope nito, of this straight line within the proportional limit ay tinatawag nating Young's modulus, or sometimes called as the modulus of elasticity. And after that point, dinaanan niya yung tinatawag nating elastic limit. And what is this elastic limit? Elastic limit is the limiting value of stress up to which the material is perfectly elastic. Ang ibig sabihin nun, within that limit, the material will return back to its original position. Meron pa siyang kakayahang makabalik sa kanyang position, sa kanyang form, sa kanyang shape when the material is unloaded. And once this stress is reached, the material can no longer return back to its original form at nagkakaroon siya ng tinatawag nating permanent deformation. Then somewhere above this elastic limit is another point which we call the yield point. Ano naman itong yield point o yield stress point? Ito naman ay tinatawag nating a stress after which the material extension takes place more quickly, with little or no increase in load. So ang ibig sabihin dito, makikita natin na mayroong paghaba yung material na wala naman siyang gaanong pag-increase ng load. Ibig sabihin nun, the material has already reached what we call yield stress point. And it can be observed by the next kay animation. Makita natin dito na humaba. Kita niyo yung humaba ito na, pero yung kanyang kay increase in the loading is very small. Ulitin natin. Okay, increase in load is very small. Somewhat you can see okay, a value here that is just okay, increase by a certain amount. Masyadong maliit lang. And there is an appreciable deformation or increase in the dimension of the material. When the material okay, has shown that behavior, ang ibig sabihin nun, the material has already reached the yield point. Then afterwards, okay, it will go up again until the material reach the maximum stress. And when that is reached, it has reached already the ultimate strength. And that ultimate strength is the maximum strength that the material have to bear, okay, before breaking. Okay, bago siya maputol, actually hindi naman siya dito mapuputol, ano? Bago siya maputol, yan yung pinakamataas na stress na mabibitbit or makikcarry ng material na yan. But after reaching that point, then the material will already fail, but it will be failing at a smaller value of the stress somewhat at this point. So this will be our ratchet point, and the material has already elongated by this amount. Okay? So yun yung ating tinatawag na stress-strain diagram. And from this stress-strain diagram, we shall be able to derive the relationship between the stress and strain so that the formula for the computation of deformation can also be taken. So from Hooke's law, which states that within the proportional limit, the stress is directly proportional to the strain. So bago ko ipakita ito, no, so banggitin ko muna, explain ko muna, ano ba itong Hooke's law at saan ito nanggaling? Actually, this Hooke's law was the concept that was formulated by Robert Hooke when he studied the behavior of the material when the material is subjected to an axial load. And he was able to come up with the relationship between the stress and strain when he observed that within the proportional limit, the stress is directly proportional to the strain. And that was the postulate made by Robert Hooke, that within the proportional limit, the stress is directly proportional to the strain. And so if we will be writing it that in symbol, we write this as stress is directly proportional to the strain. When we replace the proportional symbol with a constant, then this becomes an equation such that the stress is equal to the proportionality constant multiplied by the strain. But we know that stress is equal to P over A, and strain is equal to deformation over L. If this P over A will be substituted to this stress and deformation over L is substituted to this strain, then our formula becomes equal to PA shall be equal to E times deformation over L, and from here we can solve for the deformation such that the deformation is equal to PL over AE. So that is how we make the derivation, show the relationship between the stress and the strain. Now in this formula, okay, how do we describe the symbol or lambda is the deformation caused by the load P on the material. P is the applied load, while the length is the original length of the material. A is the cross-sectional area, and E is the modulus of elasticity of the materials. But this formula has some limitation, ano? It has to be following some assumptions when the formula was derived. And what are they? Kinakailangan masatisfy. Okay, obserbahan natin o tingnan natin ano ba yung mga condition ng ating bar o ng ating object so that we can use this formula. Dapat, una, yung material ay homogeneous and it obeys Hooke's law. Ang ibig sabihin nun, okay, the material should not be subjected to a stress more than the proportional limit. So that okay, the relationship between the stress and strain are proportional within that limit. The second one is that the load applied on the object must be along the axis of the material. That is to make sure that it causes uniform stress over the area. And the other one is that the cross-sectional area of the material is constant over the length. Dapat yung cross-sectional area ng material will be the same all throughout the length of the material. So to explain the use of formula in dealing with problem, let us have here our sample problem. Okay, sample problem number 1. A bronze bar is fastened between a steel bar and an aluminum bar as shown in the figure. So here is the figure. Okay, axial loads are applied at the position indicated. Find the largest P that will not exceed an overall deformation of 3.0 or the following stresses: 140 megapascal in steel, 120 megapascal in the bronze, and 80 megapascal in the aluminum. Assume that the assembly is suitably braced to prevent buckling. Use ESE of the steel to be 200 gigapascal, E of the aluminum at 70 gigapascal, and E of the bronze at 83 gigapascal. So I have here the bars, the composite bar that is subjected to the following loads. The bar consists of the steel, bronze, and the aluminum. The cross-sectional area are indicated such that the steel has a cross-sectional area of 480 millimeters square, while the bronze has a cross-sectional area of 650, and the aluminum has a cross-sectional area of 320 square millimeter. The lengths of the steel, the bronze, and the aluminum are given such that the steel is 1.0 meter, the bronze is 2 meters, while the aluminum is 1.5 meters. And these bars are subjected to the following loads. Okay, at the end of the steel, there is a load P acting. At the junction between the steel and the bronze, another load is directed to the right, having a magnitude of 3.0. At the junction of the bronze and the aluminum, another load is acting and a magnitude of 4P directed to the left. While at the end of the aluminum, there is a load that is acting directed to the right, having a magnitude of 2P. And from here, we are required to determine what is the magnitude of this P that would not cause an excessive stress or stress more than the steel of 140, the bronze of 120, and 80 in the aluminum. And that the total deformation of all this composite bar must not be more than 3.0 millimeter. Now to solve for this problem, let's start with defining or determining the axial load on the steel bar. Where is that steel bar? Ito yung steel bar na ito, no? So to determine the axial load on the steel bar, what we do is to pass an exploratory section anywhere in the steel bar. I-cut natin siya anywhere here, and then we isolate either the left or the right part. And when we isolate, we try to consider the one that is easier and simpler to draw. And I believe that when we take that part, we consider the left part. If this is the cutting plane or the cutting section that would cut the steel, then we consider the left part of the exploratory section, so that we have here our free body diagram of the left part of the exploratory section, so that from here we can expect that this steel will be subjected to an internal force, and we shall be calling it as P sub S. And if we are to apply the condition of equilibrium, therefore P sub S can be computed to be equal to P, which is directed away from the section. Therefore, the steel is subjected to tension. Now, if the steel is subjected to tension, saan natin that the steel will be somewhat elongated. Okay, so let us try to compute now for the value of P, without exceeding the stress in the steel of 140 megapascal. If the stress in the steel is 140, then we try to substitute it in the formula that stress is equal to PS over A. Okay, so that if stress is equal to 140, the magnitude of PS is equal to P, and the area is given to be 480, and from here we can solve for the value of P, such that I have here 140 Newton per square millimeter is equivalent to megapascal. P is actually an unknown value, while the area is in square millimeter. If millimeter square will cancel, we shall be getting the value of P in Newton, and the value is equal to 67,200 Newton. So take note that this 67,000 is the maximum value of P without okay, breaking this in terms of tension without breaking the steel. But we don't say that that is already the maximum that the entire okay, composite bar can carry, because there are two more bars that we have to consider. The other one is the bronze and the other one is the aluminum. Now let us try to consider determining the axial load on the bronze. Here is the bronze, then what shall we do? We try to pass an exploratory section anywhere in the bronze, so that when we pass an exploratory section anywhere in the bronze, then we shall have this exploratory section. Afterwards, we try to consider either the left part or the right part of the exploratory section and explore, so that we can compute for the internal force acting on the bronze. Try to consider the left part of the exploratory section, so that we show, okay, that this will be our internal force, and we call this as our P of the bronze. And by summing up, because this is in equilibrium, therefore it must satisfy the condition of equilibrium, that if we are going to apply the condition of equilibrium, that is summation of force horizontal equal to 0, we can solve for P at the bronze, which is equal to 2P. And we will see that P of the bronze is directed towards the section, therefore the bronze is subjected to compression, so that there will be a shortening on the part of the bronze. But as we have seen that if the steel is subjected to tension, there is an increase in length in the tension, while in the bronze, there is shortening on the part of the bronze. And for us to compute for the magnitude of P, that would, okay, the maximum value of P that would, can be applied without breaking the bronze, so that we can apply it in the formula that stress in the bronze is equal to P of the bronze over area of the bronze, considering that the maximum stress in the bronze is 120 megapascal, as we have seen in our problem. So if the value will be substituted in the formula that stress in the bronze is equal to 120, there is 2P as the internal force acting on the bronze, and the cross-sectional area of the bronze is 650 square millimeter. Again, from here, square millimeter will cancel, and P can be computed in terms of Newton, and we shall have here P equal to 39,000 Newton. So far we have solved two values of P. One value is when steel is being considered, and we got a value of 67,200. While the other one is when the bronze is considered, and we have a value of 39,000 Newton. But because we still also have aluminum, then we also have to consider what will be the maximum load P that can be applied considering the strength of the aluminum. So that to determine that, we determine the axial load in the aluminum bar, and that can be done by passing an exploratory section anywhere in the aluminum. So let us imagine that we pass an exploratory section here. Here is the section, and we try to consider isolating either the left or the right part of the exploratory section. But of course, I would suggest that we consider the simpler part. If we will be passing here, it will be simpler to isolate the right part of the exploratory section. Therefore, isolating the right part of the exploratory section, we will expect that this section will be subjected to an internal force that would balance the effect of the external force, and we shall be calling that as the P of the aluminum. And we will expect that P of the aluminum will be directed away from the section to balance the external force 2P here. So that if we are to apply the condition of equilibrium, that is summation of force horizontal equal to 0, we can solve for PAL equal to 2P, and that is also subjected to tension. Meaning, aluminum will also be elongated, as this would be subjected to this kind of loading. And to solve for the maximum value of P considering the strength of the aluminum with the allowable stress of 80 megapascal, therefore we substitute this in the formula that stress is equal to P over A, with stress equal to 80 megapascal, and P of the aluminum equal to 2 times of P, that is the internal load acting on the aluminum, divided by the cross-sectional area of the aluminum. Again, square millimeter here will cancel. We can compute for the value of P equal to 12,800 Newton. Now, after we have computed for that, we can make an analysis by summarizing. By summarizing the initially computed value based on the allowable stress of the materials. And let us try to make a simple analysis of these stresses. Let us try to have here our table representing what the criteria we have, the type of stress, and the maximum value P. We have if we are to consider steel, the steel is subjected to tension, and the maximum value of P that we have is 67,200. While if we are to consider the strength of the bronze, the bronze is subjected to compression, and the magnitude of the stress on the bronze is the value of P that can be applied, considering the stress of the bronze is 39,000 Newton. And if we are to consider the strength of the aluminum, which is subjected to tension, the maximum value P that can be applied is 12,800. Now, considering kung sakali lang na pag-uusapan natin ay strength ng tatlong material, malalaman natin that we can already make a decision that we can already say that it's the aluminum that will control because it's the lowest. It has the lowest value of the maximum P. But we don't have yet the final answer because the question also asks for the maximum value of P that will not exceed the overall deformation of 3 millimeters. Ang ibig sabihin nun, aside from the capacity or the strength of the material, we have to consider also ano naman yung value ng P na hindi naman mag-cause ng overall deformation of 3, considering the 3 materials that we have that are subjected to the indicated load as shown. So that if we are to consider deformation, we have to look for the value of P, and from there, saka lang tayo magde-decide ano yung ating gagamiting value. Now, solving for the maximum value of P without exceeding the total deformation of 3 mm, we consider that the total deformation must be the summation of the deformation caused by the loads on the 3 materials, that is, the deformation on the steel, the bronze, and the aluminum, considering, of course, their sense. Because the steel is in tension, there is an elongation. But because the bronze is in compression, there is shortening. And because this aluminum is also in tension, there is an elongation. So that the summation would become equal to the stress, the deformation of the steel minus the deformation of the bronze plus the deformation of the aluminum. That if the formula for deformation shall be substituted, that is equal to PL over AE. Therefore, our formula becomes, the total deformation becomes PL over AE of the steel minus PL over AE of the bronze plus PL over AE of the aluminum. That P of the steel must be the internal load which we have just computed a while ago. P of the steel is equal to P, P of the bronze is equal to 2P, while P of the aluminum is equal to 2P also. That all the other values are given in the problem, therefore we substitute the value. So that when the value is substituted, this equation becomes 3 equal to P times 1000 divided by 480 millimeter square divided by 200 times 10 cube Newton per square millimeter. This is actually equal to 200 gigapascal, because 200 gigapascal is also equivalent to 200,000 megapascal. And so when we substitute the equation, that symbol, that becomes 200 times 10 cube Newton per square millimeter. That is also true with this deformation of the bronze, that is 2P. Yung 2P nito, ito yung tumutukoy sa internal load acting on the bronze. That is multiplied by the length, by the area, and the modulus of elasticity of the bronze. Similarly, we have here for the aluminum, itong 2P yung tinatawag natin P of S, or the internal load acting on the aluminum. The length of the aluminum, area of the aluminum, and the modulus of elasticity. And because we have here an equation where P is involved, so we can solve for P, so that P becomes equal to 84,611 Newton. So that if this will now be substituted here, 84,611 Newton, so we can now make an observation and make decision of what is the maximum value of P. Balikan lang natin Kung steel ang pag-uusapan, we have 67. Kung bronze, we have 39. Kung aluminum, we have 12. At kung deformation na pinag-uusapan, we have 84,611 Newton. At dahil aluminum ay pinakamaliit na value, therefore siya yung pinaka-safe. Siya yung pinaka-safe. And that, we can have here as our conclusion that the maximum value of P is 12,000, which is controlled by the aluminum segment, whose allowable stress is limited to 80 megapascal. Yan ang ating pinakita example about how we can apply the relationship between the stress and strain, particularly the computation of the deformation in solving problems. Sana guys ay patuloy niyo ako subaybayan sa ating ginagawang discussions about this topic by subscribing to this channel and sharing it to your friends so that your friends will also be notified of my uploads. Thank you very much for watching.